Britain's most important World War II hero you've never heard of, the man who built the RAF. In 1944, 3 aircraft flew over occupied Europe that should never have existed together. A Supermarine Spitfire, elliptical wings catching the morning light above the Channel, the most beautiful fighter ever built, a product of engineering so refined that German pilots who encountered it in combat reported back to their commanders with something they rarely admitted: respect. Beside it, a de Havilland Mosquito, constructed from furniture-grade plywood and balsa wood, unarmed, carrying the same bomb load as a B-17 Flying Fortress with a crew of 2 instead of 10. And ranging far ahead of the bomber formations, a North American P-51 Mustang powered by a British Rolls-Royce Merlin engine, an American airframe, a British engine, a combination that gave it the range to escort bombers all the way to Berlin and bring them home again. 3 aircraft. 3 impossible ideas. Every senior officer in the British Air Ministry had argued against at least one of them. Most had argued against all 3. The Spitfire was too expensive and too difficult to manufacture at scale. The Mosquito was wooden, an absurdity in the age of aluminum, and flew without defensive guns, which every expert agreed was suicide. The early Mustang had been written off as a failure, useful only for low-altitude reconnaissance, not the kind of aircraft that decided air wars. One man had fought for all 3. In committee rooms and budget arguments, against skeptical generals and impatient politicians and, eventually, against a press baron with the ear of Winston Churchill himself. Not with an aircraft. Not with a gun. With memoranda and production schedules and the quiet, implacable refusal to accept that the conventional wisdom was correct. His name was Air Chief Marshal Wilfred Freeman. And almost no one alive today has heard of him. This is the story of the man who built the Royal Air Force from a museum of fabric-covered biplanes into the force that saved Western civilization. He flew no combat missions in the Second World War. He appeared in no triumph photographs. He was never the headline. He was the reason the headline was possible. By 1940, when the Battle of Britain began, Freeman had been fighting his kind of war for 4 years. And because of what he built in those 4 years, Britain had just barely enough to survive. It begins not in 1944, but in 1936, in a Britain that was bringing swords to a gunfight and hadn't yet realized it. Walk into any RAF base in 1936 and what you would see, lined up on the grass, was history. The Gloucester Gauntlet. The Bristol Bulldog. Fabric-covered biplanes with open cockpits, fixed landing gear, and 2 rifle-caliber machine guns. Aircraft of genuine elegance and no combat future. They had top speeds barely exceeding 200 miles per hour. Their pilots flew in open cockpits where temperature at altitude fell far below freezing. Their guns jammed in the cold. Across the Channel, Germany was building something that belonged to an entirely different era. Adolf Hitler had torn up the Treaty of Versailles in 1935. The Luftwaffe, which had been developing in secret for years through front organizations and overseas training programs, was now openly expanding at industrial scale. German engineers who had been constrained by treaty were free to build what they had been designing in private. The Messerschmitt Bf 109 first flew in 1935. Enclosed cockpit, retractable undercarriage, all-metal construction, a 960 horsepower Daimler-Benz fuel-injected engine. It could reach 292 miles per hour in early form. Later versions would far exceed that. Against a Gloucester Gauntlet with its 230 miles per hour top speed and open cockpit, the Bf 109 was not a competitor. It was an executioner. British intelligence was sending reports to London that senior officials found difficult to absorb. Germany was producing hundreds of aircraft per month. Britain was producing dozens. Most of what Britain built was obsolete on the day it left the factory. The RAF's planning doctrine made the situation actively worse. The prevailing belief, not fringe opinion, but official doctrine embedded in planning documents and procurement priorities, was that bombers would always get through. That no fighter force could stop a determined bombing campaign. This was not an unreasonable conclusion from the evidence available in the mid-1930s, where early fighters had often failed to intercept faster bombers and where theorists like Julio Douhet had been arguing for 2 decades that air power would be decisive in the next war through offensive bombing. The RAF had absorbed this doctrine deeply. Their planning documents called for 19 squadrons of fighters and 68 squadrons of bombers. 3.5 times as many bombers as fighters. Britain would deter attack by threatening German cities rather than defend British ones. Into this environment, in May 1936, walked Wilfred Freeman, newly appointed Air Member for Research and Development, a bureaucratic title that concealed the most consequential job in the British military. His task was simple in theory: choose the aircraft that would defend Britain in the coming war. His problem was that Britain did not yet have any aircraft capable of doing it. Freeman was 47 years old. He had served as a pilot in the First World War, commanded No. 14 Squadron, and spent the intervening decades accumulating an understanding of aviation technology and military bureaucracy that was, in the RAF of 1936, essentially unique. He was not a desk officer who had flown occasionally. He was a pilot who had watched friends die in inferior aircraft and carried those deaths with him into every procurement meeting. While other officers talked about doctrine and budgets, Freeman thought about the young men who would fly whatever he chose. That orientation, toward the pilot in the aircraft, not the aircraft in the specification, shaped every decision he made. He was also something rarer than either: an engineer's administrator. A man who could read a technical specification, understand what it actually implied, and distinguish between limitations that mattered and limitations that didn't. The RAF was full of officers who could fly and officers who could administrate. Officers who could do both, and who understood the engineering between them, were extremely scarce. Freeman looked at the planning documents, the 68 bomber squadrons and 19 fighter squadrons, and reached a conclusion his senior colleagues found heretical. Fighters would win the coming war. He could not prove this in 1936. The evidence was ambiguous, but the logic was there for anyone willing to follow it. Germany was not going to be deterred by threats. Germany was rearming precisely because it intended to use force. When that force came, what would matter was whether Britain could prevent German aircraft from reaching British cities and factories. That required interceptors. That required fighters. And the fighters Britain had were categorically incapable of intercepting anything the Luftwaffe was building. He had perhaps 2 years, 3 at most, before the war he could see coming would make careful procurement irrelevant. He began immediately. The RAF had a formal aircraft acquisition process: specification written by committee, design submitted, evaluated, winner selected, contracts placed. The process took years. Freeman had years, but not many of them, and not enough to repeat the cycle for each aircraft that might fail. He also had a deeper problem: the specifications were written by people thinking about the last war, extrapolating from existing aircraft, rather than imagining what would be needed against Germany's next generation. Freeman's solution was to work around the process. When a designer showed him something that exceeded the specifications in ways that mattered while falling short in ways that didn't, Freeman backed the designer over the committee. This was how Sidney Cam at Hawker Aircraft kept his Hurricane alive. Cam had developed a monoplane fighter using construction methods that were, by 1936, traditional: a metal tube framework covered with fabric and doped to provide rigidity and smoothness. The technique was familiar to every manufacturer in Britain. Workers knew how to build it. Mechanics knew how to repair it. A damaged Hurricane could be patched in the field and returned to combat within hours, a tactical advantage that would prove critical in the summer of 1940 when squadrons were losing aircraft faster than replacement deliveries could arrive. But some voices in the Air Ministry wanted all-metal stress skin construction, the technique being developed in America, arguing it was structurally superior and aerodynamically cleaner. Freeman's calculation was direct: the Hurricane could be in squadron service within 2 years, using factories and workers that already existed. All-metal construction would require retooling factories that didn't have the equipment, retraining workers who didn't have the skills. A slightly inferior aircraft available in 1938 was worth immeasurably more to a nation that might be at war in 1939 than a technically superior aircraft available in 1942. Speed to deployment outweighed marginal performance gains. He pushed the Hurricane through. Then there was the Spitfire. Reginald Mitchell, chief designer at Supermarine, had been working on a high-performance fighter since 1934, a private obsession as much as a professional assignment. The aircraft that emerged, designated Type 300, was unlike anything else on the drawing board or in the air. All-metal stressed skin construction. A Rolls-Royce Merlin producing over 1,000 horsepower. And the defining feature: an elliptical wing of extraordinary aerodynamic refinement, thin enough for high speed, large enough for adequate maneuverability at lower speeds, capable of housing 8.303 caliber Browning machine guns in its leading edges while maintaining the clean lines that gave the aircraft its performance. The elliptical planform had been used in aircraft before, but never quite like this. It was Mitchell's solution to a difficult optimization problem, and it was beautiful in the way that solutions to difficult optimization problems sometimes are. Mitchell was dying as he designed it. Cancer had been diagnosed before the Spitfire flew, and he knew, with the particular clarity that terminal illness provides, that he was racing his own body. He worked through the pain because the work was worth finishing. The Spitfire made its first flight on March 5, 1936, 4 years before the Battle of Britain it would help win. Mitchell saw it fly. He died on June 11, 1937, 14 months later, at the age of 42. He never saw his aircraft in combat. The Spitfire was expensive. The elliptical wing was a manufacturing nightmare, complex double curves requiring precision metalwork that most British factories didn't have the tooling or the skilled labor to produce. Every Spitfire cost more and took longer to build than any comparable aircraft. Some in the Air Ministry wanted to cancel it. Not because it wasn't extraordinary, anyone could see it was extraordinary, but because the same resources could build more Hurricanes, and more was better than best if you were facing a numerical threat. Freeman refused. Here is the decision that saved Britain. He ordered both. Not the Hurricane because it was cheaper. Not the Spitfire because it was better. Both, because he understood what the Air Ministry committees had missed. A modern Air Force is not a single aircraft type. It is a system of complementary capabilities. The Hurricane would be the workhorse, reliable, available in numbers, easy to repair, structurally robust enough to absorb combat damage and continue flying, and devastating against German bombers which were, after all, the threat that mattered most to British survival. The Spitfire would be the thoroughbred, fast enough to catch German fighters, agile enough to win the turning fights that determined who controlled the sky, good enough that Luftwaffe pilots encountering it for the first time would report back with something they rarely admitted about Allied aircraft, that it was their equal or better. Together they were more than the sum of their parts. The Hurricanes engaged the bombers. The Spitfires engaged the fighter escorts. 2 aircraft, 2 roles, 1 coherent tactical system. Freeman had seen the combination at a moment when everyone else was arguing about which single type to procure. An aircraft is only as good as its engine. Both the Hurricane and the Spitfire flew on the Rolls-Royce Merlin, a liquid-cooled V12 that was, by the mid-1930s, the finest aero engine in Britain and arguably the finest in the world. The Merlin had its origins in the PV-12, a private venture Rolls-Royce had developed from 1933 onward without government funding, because the company believed the RAF would need it even before the RAF was convinced it did. By 1935, the engine was producing over 1,000 horsepower from 27 litres of displacement. By 1940, the Merlin III was developing 1,030 horsepower. By 1944, the Merlin 66 was producing 1,705 horsepower from the same basic architecture, a testament to the sustained engineering development that occurred across the war years. The Merlin powered not just the Spitfire and Hurricane but the Lancaster bomber, the Mosquito, the Halifax, and ultimately the Merlin-Mustang. It was the engine of the RAF's war. But Rolls-Royce was a small company, operating from a single major facility in Derby. At full stretch, their works could produce Merlins at a rate measured in single digits per week. Freeman's aircraft orders required Merlins at a rate measured in dozens per day. The arithmetic was straightforward and terrifying. You could order all the Hurricanes and Spitfires and Mosquitoes you wanted. Without engines to put in them, they were expensive aluminum sculptures. Freeman's solution was government-funded shadow factories, facilities built specifically to produce Merlin engines in parallel with Rolls-Royce's own production, using government capital rather than Rolls-Royce investment, staffed with workers trained specifically for the purpose. The terminology was deliberate, a shadow of the parent company's expertise, replicating its output without requiring the decades of institutional development that had produced the original. The Rolls-Royce Shadow facility in Crewe began production in 1938. Ford's Merlin plant at Trafford Park, Manchester, would eventually produce Merlins at rates that Derby alone could never have approached. Between these facilities and Rolls-Royce Derby, Merlin production reached the scale that wartime requirements demanded. Rolls-Royce had legitimate commercial concerns about their proprietary engine designs being manufactured outside their direct control. Quality standards, labor practices, post-war competitive implications. Freeman negotiated these concerns respectfully while making clear that the arithmetic of the situation left no alternative. Private production rates applied to wartime requirements was not a survivable equation. The shadow factories were approved. The same model applied to airframes. Castle Bromwich, near Birmingham, was designed specifically to produce Spitfires at a scale the Supermarine facility at Southampton could never approach. When operational, it would multiply Spitfire output by an order of magnitude. When operational, in May 1940, it had not produced a single aircraft. By May 1940, Castle Bromwich had not produced a single Spitfire. Not one. After 18 months of construction, government investment, public fanfare, and national expectation, the factory that was supposed to multiply Spitfire production had delivered 0 complete aircraft. The building existed. The equipment had been installed. The workers had been hired and nominally trained. The factory was, in every visible sense, operational. And it had produced nothing. The facility had been handed to Lord Nuffield, William Morris, automobile manufacturer, elevated to the peerage for building a British car industry. Nuffield was a capable industrialist. But Spitfires were not motorcars. The tolerances were different. Aircraft aluminum skin required dimensional accuracy measured in thousandths of an inch. The jigs, precision frameworks holding components in alignment during riveting, had to be engineered specifically for each aircraft assembly, and Nuffield's team had configured them incorrectly. They applied automotive production logic to an environment that rejected it at every point. Capable people, systematically misapplying genuine expertise. 0 aircraft. Freeman had been raising alarms for months, reports filed. Management changes requested. He was trapped. He could advise on production direction but could not reach into a contractor's factory and reorganize its management. He could see the problem with perfect clarity and lacked the formal power to fix it. On May 10, 1940, Germany invaded France. By June 22, France had surrendered. Britain stood alone. Fighter Command was losing aircraft over Dunkirk faster than production could replace them. Every Spitfire Castle Bromwich should have been building and was a Spitfire a British pilot didn't have. Churchill became Prime Minister on May 10, the same day Germany invaded France. He created the Ministry of Aircraft Production and appointed Lord Beaverbrook. Beaverbrook received sweeping powers and a single priority: produce aircraft, by whatever means necessary. Beaverbrook telephoned Nuffield. The conversation was brief. Nuffield began explaining the difficulties. Beaverbrook interrupted, told him he was taking immediate control of the factory, and when Nuffield began to protest, hung up. Within days, Beaverbrook had installed Vickers Armstrong's management, people who had been building Spitfires at Southampton from the start. He ran the factory 7 days a week and personally toured it to demolish anyone offering excuses. In July 1940, the factory produced its first Spitfire. In August, 37. In September, 56. Churchill called it miraculous. Beaverbrook became the hero of British aircraft production. Here is what the press did not report. The production surge was Freeman's infrastructure finally operating as designed. The shadow factories Freeman had commissioned. The production lines Freeman had organized. The capacity Freeman had spent 4 years building. Beaverbrook had removed the Nuffield obstruction. Freeman built the river. Beaverbrook cleared the dam. The headlines celebrated Beaverbrook. Freeman was moved to Vice Chief of the Air Staff in November 1940, formally a promotion, practically a removal from aircraft production. In October 1942, he was brought back. And in the 2 years since he had left, one program he had started in 1938 had survived every attempt to kill it. In 1938, Geoffrey de Havilland came to Freeman with an idea the Air Ministry found somewhere between eccentric and irresponsible. Build a bomber from wood. Not aluminum. Not steel. Furniture-grade plywood and balsa, the materials of cabinet makers and piano manufacturers. Make it fast enough, over 400 miles per hour, that it doesn't need defensive gun turrets. Fly it with a crew of 2, pilot and navigator. No gunners. No turrets. No defensive hardware of any kind. 2 Merlin engines, a wooden airframe, and speed. The Air Ministry's bomber specifications assumed that any aircraft entering German airspace would be intercepted. The defensive armament requirements, gun turrets, gunners, the weight and drag and complexity and mechanical unreliability they entailed, flowed directly from that assumption as a logical necessity. Remove the defenses and you removed survivability. Every bomber expert in Britain and America agreed on this. The principle had been validated in combat repeatedly. An unarmed bomber was not a bomber. It was a target. De Havilland was proposing to make it fast enough that it couldn't be caught. The Air Ministry commissioned studies. The analyses were rigorous. De Havilland's performance projections were impossible. The committees concluded, no twin-engine aircraft of the proposed weight could achieve 400 miles per hour. Wood would warp and delaminate in the humidity of tropical operating environments. The glued construction would deteriorate under operational conditions. Wood was a material for garden furniture and violins. not modern aircraft. This was 1938, not 1918, and the age of wooden aircraft had passed. Freeman read the studies. Then he ran the numbers himself. The aircraft would be constructed from materials Britain had in abundance and could source domestically, furniture-grade plywood, balsa from suppliers already in the supply chain, without touching the aluminum allocation that was simultaneously required for Spitfires, Hurricanes, Lancasters. The entire metal aircraft production pipeline. Britain's war had devastated the civilian furniture market. Cabinet makers had no civilian orders. Piano manufacturers had empty workshops. Thousands of highly skilled woodworkers, people who could work to precise tolerances, who understood grain orientation and lamination and finishing, were largely idle, their skills irrelevant to the metal aircraft industry that had absorbed every other manufacturing worker. Metal aircraft needed aluminum. Aluminum was scarce, contested between programs, imported at considerable cost through supply chains that German submarines were actively trying to disrupt. Every Mosquito built from wood was a Mosquito built without consuming any of that allocation. The supply chain logic was elegant. Build the aircraft from the materials you have in abundance, free the scarce materials for everything else. Then the performance question. Freeman analyzed the power-to-weight ratio of the proposed design. He examined the aerodynamic efficiency, the clean lines, the absence of turrets and external hardware that created drag, the careful shaping that de Havilland's team had produced. He calculated what the Merlin engines could achieve without the weight and drag of defensive systems. The math was not conclusive in the direction the Air Ministry studies had indicated. De Havilland might be right. And if de Havilland was right, the implications cascaded in every direction. A bomber that could genuinely outrun German interceptors needed no gun turrets, not as a theoretical nicety but as a real operational fact. A bomber without gun turrets saved hundreds of pounds of structural weight plus the weight of the turrets themselves, the gunners, their equipment, their ammunition, the hydraulic or electric systems that drove the turrets. Hundreds of pounds of saved weight meant more fuel, more bombs, more range. The entire defensive philosophy of bomber design, weight spent on protection, was predicated on the assumption that you would be caught. Remove that assumption and the whole calculus changed. Freeman placed an initial order for 50 aircraft. The project proceeded. Then France fell, and Beaverbrook arrived, and Beaverbrook looked at the Mosquito program and made an immediate judgment. Waste. Britain needed fighters now and heavy bombers for the long-range campaign later. An experimental wooden aircraft 2 years from operational service was a diversion of resources the country couldn't afford. He ordered it cancelled. Freeman didn't cancel it. Not through open defiance. Beaverbrook was too politically powerful and Freeman too skilled a bureaucrat for that. Freeman simply didn't pass the cancellation order down the chain. The de Havilland team continued working. When Beaverbrook discovered this, months later, the prototype was nearly complete. Beaverbrook was furious. He called it Freeman's folly. Every skeptic in the ministry adopted the name as a convenient shorthand for the proposition that Freeman's judgment on unconventional programs was not to be trusted. The prototype flew on November 25, 1940. 380 miles per hour. Later versions exceeded 400. It could carry a 4,000-pound bomb to Berlin and return to England, the same bomb load as a B-17 Flying Fortress, delivered by 2 men instead of 10, built from wood by cabinet makers who needed no aluminum allocation. The Mosquito became one of the most versatile aircraft of the entire war. High-speed bomber, night fighter, photographic reconnaissance platform, pathfinder for bomber command, fighter bomber, maritime patrol aircraft. It flew faster than the German interceptors sent to catch it. Its wooden construction, declared a fatal weakness by the Air Ministry studies, turned out to be a practical advantage. Woodworking factories across Britain manufactured components that no metal aircraft facility could produce, expanding production capacity into an entirely different sector of British industry. Piano manufacturers built wing sections for the aircraft that Goring, in a moment of barely contained fury, described as a source of boundless shame, that Britain was building effective bombers from wood while Germany was supposed to lead the world in aviation. Freeman had called it correctly when everyone else called it impossible. He had protected it through bureaucratic obstruction when Beaverbrook tried to kill it. Freeman's folly became one of the decisive aircraft of the Second World War. By late 1943, the strategic bombing campaign against Germany was approaching a moment of crisis that threatened to end it entirely. The 8th Air Force was flying B-17 Flying Fortresses and B-24 Liberators into German airspace in daylight. The American doctrine of precision bombing required seeing the target, which required daylight, which meant flying through the full strength of German fighter defenses in conditions where the attackers could be seen from miles away. The losses were accumulating toward unsustainable levels. The October 14, 1943 mission to Schweinfurt, the second raid on the German ball-bearing industry, sent 291 B-17s deep into Germany. 60 were destroyed. 17 more were damaged beyond repair. 594 American airmen were killed, captured, or missing. Nearly 1 in 4 attacking aircraft did not return. The 8th Air Force suspended all deep penetration missions while its commanders considered whether daylight strategic bombing was operationally feasible at all. The problem was range. Bombers needed fighter escort to survive German interceptors. This had been established beyond any doubt by the loss rates of unescorted formations. But no fighter had the range to accompany bombers all the way to their targets and back. Fighters needed maneuvering fuel, reserves for climbing, diving, turning in combat, that bombers flying straight and level didn't consume at the same rate. A fighter that arrived at the target with enough fuel to fight effectively had to break off and return before the bombers completed their runs. German fighter controllers knew the range limits of every Allied escort type and briefed their pilots accordingly. Wait for the P-47 Thunderbolts to turn back. Then attack the unprotected bombers. The system worked with brutal efficiency. There was an American aircraft that looked, in theory, like a potential solution. The North American P-51 Mustang had one of the most aerodynamically efficient airframes ever produced. The laminar flow wing and carefully shaped fuselage were the product of exceptional design work, genuinely advanced for their time. North American had created a low-drag airframe that, properly powered, had range potential that no other fighter in the inventory could approach. The Mustang's problem was its engine. Production Mustangs used the Allison V1710, an American engine that performed adequately at low altitude but lost power dramatically above 15,000 feet, precisely the altitude where bomber escort missions were flown. An Allison Mustang at 25,000 feet was a mediocre fighter, outclimbed and outperformed by the German fighters it was supposed to be protecting bombers against. The RAF had evaluated early Mustangs and found them useful for low-level tactical reconnaissance and ground attack, roles that suited their low-altitude capabilities without requiring them to operate at heights where they were outclassed. The Americans were losing interest. The P-51 was being increasingly written off as a category error, a beautiful solution to a problem that didn't require a solution. Freeman looked at the Mustang airframe and saw something different from everyone else's assessment. He saw aerodynamics that were, in certain respects, better than the Spitfires. The laminar flow wing produced less drag at cruise conditions, which meant more range on the same fuel load. He saw a fuselage volume sufficient to carry the fuel loads that long-range escort required. He saw, in the fundamental physical architecture of the aircraft, a potential that the Allison engine was preventing from being realized. And he knew an engine that had solved the high-altitude performance problem for every aircraft it had ever been fitted to. He arranged for Rolls-Royce Merlin engines to replace the Allison V1710 in a series of test aircraft. The first Merlin-Mustang flew in October 1942. The results were not subtle. A Merlin-powered Mustang could fly at 437 miles per hour at 25,000 feet, with dramatically greater range than the Spitfire. With drop tanks it could escort bombers from England to Berlin and back, the range German air commanders had been certain no Allied fighter would ever achieve. The 8th Air Force placed orders by the thousands. Those Mustangs flew escort from early 1944 onward. German fighter pilots who had been reliably waiting for the escorts to turn back found the Mustangs staying with the formations all the way to the target and all the way home. The tactical certainty that had made German defense of German airspace manageable, exploit the range limit, let the escorts leave, then hit the unprotected bombers, was simply gone. The Luftwaffe's fighter force was ground down in attrition battles. It could not sustain at the pace the combined Allied bomber offensive was imposing. By June 1944, when the Normandy landings required Allied air superiority over the beaches and the approach routes, German air defenses had been degraded to the point where they could not effectively oppose the landing. The subsequent Allied campaign against German oil infrastructure, refineries, synthetic fuel plants, the supply chain that kept German armor and aircraft operating, could only be conducted once German fighters could no longer oppose it in strength. That campaign crippled Wehrmacht fuel supplies for the remainder of the war. One engine swap. Freeman's idea. The aircraft that the Americans were writing off as a useful low-altitude platform became the decisive long-range fighter of the European air war because one man had looked at its airframe and seen what it could become rather than what it currently was. There is a set of statistics from the Battle of Britain that historians cite routinely, and that most listeners find counterintuitive when they first encounter them. In June 1940, when the battle formally began, the RAF had just over 600 operational single-engine fighters. The Luftwaffe had more than 750 single-engine fighters, plus twin-engine Bf-110 fighters and a substantial bomber force. Germany held clear numerical advantage at the start. By October 1940, when the Luftwaffe acknowledged failure, when Göring's staff concluded that the Luftwaffe had not achieved air supremacy over England, that Fighter Command had not been destroyed, and that Operation Sea Lion could not proceed on the planned timeline, the RAF had 732 operational fighters. The Luftwaffe's single-engine fighter strength had fallen to approximately 275. The RAF ended the battle with more fighters than it had at the start. Despite having lost, by official count, 1,087 aircraft destroyed during 3.5 months of some of the most intense aerial combat in history. The production system was replacing aircraft faster than combat was consuming them. The shadow factories that Freeman had commissioned. The standardized manufacturing processes. Castle Bromwich, finally functional after Beaverbrook removed the Nuffield obstacle, contributing Spitfires at the rate it had always been designed to produce. The Merlin production at Crewe and Trafford Park providing engines to match the airframe output. The entire system that Freeman had spent 4 years building from nothing was doing, in 1940, exactly what it had been built to do. While the RAF was losing aircraft to German guns, British factories were building replacements at a rate that exceeded the loss rate. While the Luftwaffe was also taking losses, heavier losses than its commanders had anticipated, flying over hostile territory where a shot-down German pilot became a prisoner while a shot-down British pilot climbed into a replacement aircraft, German production was replacing their losses more slowly. The Luftwaffe entered the battle with numerical advantage. It exited with a fraction of its starting strength. The reversal wasn't visible day by day. It accumulated invisibly, over weeks of combat, in the aggregate of individual production decisions made in factories across the Midlands and the South. At the battle's start, Germany had numerical superiority. At its close, Britain had it. That shift happened not primarily in the sky above southern England, but on the factory floors that Freeman had built. The pilots of Fighter Command were essential and irreplaceable. Their courage, their skill, their endurance through weeks of combat that reduced men to exhaustion and then asked them to fly again, all of this was real and necessary and, in the most direct sense, was what prevented Britain from being invaded. Without them, no production system would have mattered. 600 aircraft without men willing to fly them are parked machines. But without the production system, their courage alone would not have been enough. 600 aircraft fighting 750 cannot win through courage alone, however extraordinary that courage is. 732 fighting 275 can win through courage combined with the industrial capacity to sustain the fight. Freeman provided the industrial capacity. The Battle of Britain is remembered as the triumph of the few. It was also the triumph of a system that one man had built before anyone else understood why it was needed. Freeman was formally promoted to Vice Chief of the Air Staff in November 1940, removed from aircraft production at the precise moment his system was demonstrating what it could achieve. He returned to the Ministry of Aircraft Production in October 1942 and remained until the war's end in 1945, guiding production through the sustained strategic campaign phase that followed the immediate survival crisis. He received no newspaper profiles. He gave no interviews. When Churchill praised the miraculous production surge of summer 1940, Beaverbrook received the credit. When the Mosquito became one of the war's most celebrated aircraft, de Havilland received the recognition. When the Merlin-Mustang transformed the air war over Europe, the story was told, accurately, in its parts, as American engineering meeting British engine manufacturing without noting that the combination had been Freeman's idea from the beginning. He retired in 1945, was made a baronet, Sir Wilfred Freeman, and received the honours appropriate to a senior officer of his rank and length of service. He never wrote a memoir. He gave no retrospective interviews. He made no effort to establish the historical record of his contributions in competition with the more visible figures who had received credit for what he had built. He died in 1953 at the age of 64. His nephew, Air Commodore Anthony Furse, wrote a biography in 1999, Wilfred Freeman, the genius behind Allied survival and air supremacy. It is one of the few places where Freeman's complete story has been told in full. Most histories of the RAF and the Battle of Britain mention him in passing if at all, because history has always had a bias toward the visible. The pilot in the cockpit, G-forces pressing him into his seat as a Messerschmitt fills his gun sight, is visible. The official in a ministry office, Winning an argument about production specifications for an aircraft that won't fly for 3 years is not. History records what can be seen and photographed. Freeman worked in the passive voice, in the subordinate clauses, in the long-term consequences of decisions whose effects took years to materialize. What he left behind was the aircraft. Every Spitfire that flew in the Battle of Britain. Every Hurricane that broke up a German bomber formation over the Channel. Every Mosquito that flew a precision raid through German defenses and returned without a scratch. Every Merlin-Mustang that escorted a B-17 formation to Berlin and brought it home intact. Freeman didn't design any of them. He didn't fly any of them. He was the man who decided they would be built, who fought for the resources, who protected the programs that would have been cancelled by more cautious or more politically constrained minds. Consider the counterfactual, because it is worth sitting with. If Freeman had accepted the bomber doctrine of 1936 and allocated resources accordingly, Fighter Command would have faced the Battle of Britain with fewer, less capable aircraft. Whether Britain could have survived with Gauntlets and Bulldogs facing Bf-109s is not a serious question. It could not have. If Freeman had ordered only the Hurricane and cancelled the Spitfire as too expensive, the RAF would have fought without the aircraft that Luftwaffe pilots genuinely feared, the one they reported back about, the one that forced German fighter tactics to change. If Freeman had passed Beaverbrook's cancellation order to de Havilland, the Mosquito would never have existed. The precision raids, the night fighting, the photographic reconnaissance, the pathfinding, gone. If he had accepted the consensus judgment on the early Mustang, deep penetration bombing would have remained impossible well past 1944. Any one of those failures changes the war in ways ranging from costly to catastrophic. Freeman made none of them. The Battle of Britain is remembered as the triumph of the few, the 544 RAF aircrew who died defending Britain, the thousands more who flew until exhaustion. Their courage was real, irreplaceable, and deserves every tribute it has received. They were the few. Behind the few was one man who spent 4 years making sure they would have something to fly. Freeman never flew a Spitfire in combat. He ensured that other men could. He fought the battles that had to be won years before the shooting started. He built the system that made survival possible in the weeks when survival was genuinely in doubt. He is the genius behind Allied survival and air supremacy. His name has been known, for most of the 8 decades since the war ended, only to specialists. Now you know it too.